Okay, so we're back and we're delighted to have David Turton, who's going to be talking about the ADS3 holography and microstate geometries, I guess. And over to you, David.
Okay, thank you very much. Thanks for the invitation. It's a pleasure to be speaking at this very nice mini conference. And today I'm going to tell you about indeed ADS3 holography based on a couple of works, the first of which with Stefano Giusto and Sami Rawash, my PhD student, and the second of which should appear hopefully very soon with Sami. So let me start by echoing the enthusiasm of today's speakers that we live in very exciting times physics-wise. Amidst all the chaos going around in the rest of the world, it's actually a very exciting time in black hole physics, and the time is ripe to further the exploration of the internal microstructure of black holes in light of recent experimental advances. With that said, today's talk, my talk is going to be purely theoretical and not motivated, not connecting directly with experiment. I'm going to be interested in exploring holography as a tool to identify the microscopic interpretation of a given configuration in the bulk. And in today's talk, all of those configurations are going to be supergravity solutions. So if we're given a supergravity solution and we want to know how we should interpret it microscopically, identifying a dual CFT state is an excellent way of doing so. Of particular interest are the supergravity solutions known as superstrata. These are proposed to be holographically dual to heavy pure CFT states and indeed are coherent, pure, and interpreted as black hole microstates. These black hole microstate geometries, as they're known, provide examples of string theoretic quantum structure on the scale of the black hole event horizon. And we've heard already a little about that today. These microstate geometries, as many of you know, are interpreted in the context of the broader fuzzball proposal that quantum effects are important on the scale of the would-be horizon due to the finite size of the underlying quantum bound state and such that Hawking radiation is unitary. And if this could be established in general, this would resolve the black hole information paradox. In today's talk, I'm going to talk about three-point functions, three-point correlation functions, which consist of expectation values of certain light operators in heavy background states. So the heavy backgrounds are these geometries, and the light operators are going to probe the geometry. In the holographic CFT, this terminology of light and heavy means that we'll be working at large central charge C, and the light operators will have conformal dimensions of order 1 with C, while the heavy operators will have conformal dimensions scaling like C. And so denoting the heavy state by H and some set of light operators by OI, we're interested in correlators of this form, which will be protected quantities such that we can compare them between the CFT and the gravity. To note, it's the case that for sufficiently typical microstates in some appropriate ensemble, the correlators of these light operators are going to be exponentially well approximated by the ensemble average values, so they don't contain too much information on typical states. However, they do contain a lot of information about atypical states, and we're going to be considering specific families of atypical states in this talk. And this will allow us to investigate and probe the proposed duality between these CFT states and these families of microstate solutions. So the motivation for this work is these microstate solutions known as superstrata, and in particular, some of the most recent such superstrata, which are known as supercharged superstrata, and we'll discuss why these are called supercharged very soon. And in order to undertake these holographic studies, we'll need to actually refine and extend the precision holographic dictionary to new sectors of these light operators in order to actually compute these three-point functions. In order to do that, we're going to need to resolve the mixing between single trace and multi-trace operators in the CFT, which is a long-standing problem. Okay, some of the talk towards the end is going to involve some technical details, and I'm aware that not everybody in the audience is an expert on these things. So let me give the take-home message right now, and then we can see the details in due course. We will refine and extend this precision holographic dictionary to new sectors of these light operators, resolving this mixing between single and multi-traces. Using this new precision dictionary, we're going to perform precision holographic tests of this proposed duality between superstrata and certain CFT states, families of CFT states. And we're going to find a highly non-trivial and quite elegant agreement between gravity and CFT. And please feel free to interrupt as we go along with questions and comments. This is my outline. So we're first going to introduce the relevant background primarily for the non-experts, and also to set up some notation. Then we'll review superstrata very, very briefly, including their supercharged versions. Then we'll discuss this mixing between single and multi-traces, and then we'll go into the results on the holographic dictionary and testing the supercharged superstrata and their holographic description. Okay, so we're going to work in Type 2B string theory with a compactified on a four-dimensional manifold, which will be T4 or K3. We'll be working with T4 for concreteness, but we'll also keep K3 in mind. Not much is going to depend on that distinction. We'll also have an additional compact circle S1, which will be have coordinate Y, and then the remaining directions are a 4+1 Minkowski space a priori. So the radius of S1 will be Ry, and we'll wrap N1D1 branes on the S1 and 5D5 branes, excuse me, D5 branes on S1 times T4, and we'll have NP units of momentum along S1. And for states which have geometrical descriptions, the geometry has dimensional charges proportional to these numbers of branes, these integer numbers of branes and momentum. So as is standard, we can take an ADS3 decoupling limit in which these geometries, if we have a geometrical description, have instead of this flat asymptotics, instead an ADS asymptotics, which is this ADS3 times S3 times T4, which is 1 then. On the holographic side, the world volume gauge theory on the bound state flows in the infrared to a 1+1 dimensional 4,4 superconformal field theory, which is a deformation of a symmetric product overfold theory with target space, the symmetric product of T4. And the number of copies of the T4 is the product of the number of D1 branes and the number of D5 branes. So this is one of the original examples of holography. It's been very well studied. It's a weak, strong duality. However, protected quantities can be compared between gravity and the CFT. And on the CFT side, we're going to work at the orbifold point. So let me review a few facts about this theory. We have n copies of a C = 6 T4 sigma model. Each copy has 4 bosons, which we'll call X, and 4 left-moving fermions plus 4 right-moving fermions, psi and psi bar. The theory also has twist operators, which permute these fields and link together effectively different copies. So as you go around a twist operator, fields of different copies have their boundary conditions mapped into each other. And this effectively leads that sector to be effectively a single CFT on a circle k times longer. So if we have a twist operator of degree 3, we take 3 copies of the CFT and the boundary conditions get wound together. And this is commonly known as being a strand of length k. The symmetries of the CFT are Virasoro left and right, of course, 4,4 supersymmetry. The R symmetry is SU2 left times SU2 right, and we have various indices. This is just to introduce some notation. The details are not going to be super important, so don't worry if you're not familiar with this theory. We also have an organizational SO4, which gives us another copies of SU2 from the T4. And one of these SU2s, the custodial symmetry, appears in the superconformal algebra, and the other one is a spectator for today. So the superconformal algebra generators then have Virasoro left times right, SU2 currents, J and J bar, and importantly for today, the 4,4 supercharges G, 4 on the left and 4 on the right. So each of these indices, alpha and A, have values plus or minus. So it's a two-dimensional index. So 2 times 2 gives us 4 left and 4 right. Okay, so of primary interest is going to be the short multiplets of the theory. So these are, if we have a state or an operator with eigenvalue h under L0, so weight h, and spin m under J3, then the J3 eigenvalue m, if you like, then a chiral primary on the left is simply annihilated by G plus minus a half, and this is equivalent to the statement that m equals h. So if you start with the chiral primary, then you can fill out a short multiplet by acting with these global generators of the anomaly-free subalgebra of the symmetry algebra, and then you get sort of various components of the short multiplet. Equivalently, but with slightly different conventions, we could simply consider anti-chiral primaries, where instead of G plus minus half, we choose to act with G minus minus a half, and this is equivalent to m equals minus h. And then we would fill out the short multiplet by acting, instead of J minus, we'd just act with J plus, and so on. So that's just a choice of convention, but for today, it's more convenient to use conventions where we use anti-chiral primaries and then fill out the short multiplet with these operators. So these chiral primaries are related on the spectral flow to Ramon-Ramon ground states. There are 5 bosonic T4 invariant ground states in each twist sector, which are labeled by their charges onto SU2 left times SU2 right, which can be plus a half, minus half, or 0. And so there are 4 here and 1 here. And the 0,0 state is actually invariant under all symmetries. It's an important player in today's talk. These states are the spectral flow of anti-chiral primaries in the NS sector in my conventions. And so this plus plus ground state, which was one of these 4, is mapped by spectral flow to the global vacuum in the NS sector. And this 00K Ramon ground state is mapped on the spectral flow to operator, which is anti-chiral on both left and right in the twist sector K. So we're going to work in the NS sector today, so we're going to be dealing with these kind of objects. Okay, that was a lightning review of some background material. So probably that was very familiar to experts and probably too quick for non-experts, but hopefully we can use that as a basis for talking about superstrata. So a superstratum, quite generally, is a supergravity solution that is horizonless, smooth up to possible orbifold singularities, supersymmetric, asymptotic to a large classical black hole, and importantly, it depends on arbitrary continuous functions which describe some back-reacted supergraviton waves. And these can be constructed with this flat asymptotics, or we can work directly in the decoupling limits with the asymptotics of ADS3 times S3 times T4. And in this talk, we're going to study holography, so we'll work fully in the ADS3 decoupling limit throughout. And as we heard in Ben's talk, these structure of these solutions is that the solution resembles the BTZ black hole throughout the majority of the solution until you get quite deep inside the geometry, where we have some microstructure in the form of these back-reacted waves, allowing the solution to cap off smoothly. Okay, so the construction of the superstratum solutions has progressed over the last several years. The simplest first families of superstrata that were constructed are proposed to be holographically dual to CFT states that I'll now describe. So we have n copies of the CFT, and we're going to put some of those copies in the NS vacuum with just a single winding, completely unexcited string. That's a strand which doesn't carry any of the momentum charge. Another type of strand that's going to be present in the state is going to carry momentum charge through these excitations here. and is going to be built on this operator, this anti-chiral primary, which was related to the 0, 0 strand in the Ramon-Ramon sector. And the parameters of these excited states are KMN, where K labels the twist of the chiral primary we start with, and M and N label these excitations, which give us the various descendants in the short multiplet. And these KMN, by the way, are exactly the 1, 0, N that Ben mentioned in his talk. That's one simple, relatively simple family of these solutions, which is not quite, I would say, the spherical cow that Ibu was asking for. That would be an absolutely really simple solution. However, they are quite nice and fairly simple. They're like a fairly bumpy spherical cow, but they've facilitated a lot of study in following works because of their nice properties such as integrable geodesics. Okay, so this is something to have in mind as one family of these superstrata. It's not the most general thing. In general, we could have different strands of these types, different types of excited strands with different parameters, K1, M1, M1, K2, M2, N2, and so on, with some specific set of coefficients. And each of these excited strands corresponds to one of these supergraviton waves in the geometry under the proposed duality. So the supergravity description is expected to be good at large n and when the average numbers of each strand are of order n. And we make a coherent state then with all these types of both non-excited and excited strands. And at large n and under these conditions, then the coherent state is sharply peaked around the average numbers of each strand. So in supergravity, then the general structure is some set of back-reacted multi-supergraviton waves starting from various seed solutions. I've given you one example here. And many families have been constructed and studied over the past several years. This is an incomplete list of authors, and I simply ran out of space because lots of people have worked on this, including Ben's group from Brussels that we heard about earlier today. Okay. On the supergravity side, I'm not going to say too much because the time doesn't allow today, but the broad outline of how you go about constructing these solutions involves solving a set of layered BPS equations in sequence for type 2b supergravity ansatz data, which involves some one-form beta, a four-dimensional base metric, and then a set of scalars zi and two forms theta I. And then finally, the final layer is for a scalar f and a one-form omega. And so these brackets denote the various layers of equations that you solve. So you first this layer first, and this will be the second, and then this is the final layer. When you're solving these equations, a solution to the first two layers typically has a number of unfixed parameters, which are essentially Fourier coefficients of these back-reacted supergraviton waves. And then solving the final layer of equations and imposing smoothness gives rise to algebraic relations on these parameters. And this procedure in general is known as coiffuring. And the requirements for smoothness in constructing these solutions, from the supergravity side, you go through a procedure and you get some algebraic relation. But the relation that comes out a priori seemed quite mysterious and in certain examples highly elusive. In particular, when some particular combination of parameters in, let's say, a two-mode superstratum was non-zero, and this puzzled us for quite some time. This puzzle was resolved in the last few years by considering an enlarged set of states known as supercharged superstrata, and this involves not just the excitations under these bosonic generators J0 plus and L minus 1, but also a particular combination of two supercharges with this extra J0 plus L minus 1. And this particular linear combination is simply there to give rise to an orthogonal state. So this, if you acted just with GG, you would have some admixture of this extra part. So you simply subtract that out to get an orthogonal state, which then corresponds to an independent supergravity excitation. Okay, so then combining, so these set of states had a more general supergravity ansatz in the bulk, and combining the fields and the ansatzes that are turned on for the supercharged superstrata, also for the original superstrata, in a couple of nice papers, a more general coiffuring strategy and relations were developed. So this resolved this problem of the elusive modes in the non-supercharged superstrata. And by now we have some very general multi-mode coiffuring relations, which are now under very nice control in the supergravity. And so one part of this talk is going to be to provide a CFT insight into this more general coiffuring. So the CFT can give you an insight into what fields are turned on and also into this coiffuring. And this is kind of how the CFT knows about the requirements of smoothness in the gravity side. Okay, any questions so far? Okay, if not, let me proceed. So a general question you could ask, and was asked in early days of holography, is suppose I have a state in the bulk which consists of a single particle supergravity excitation. So what is the dual CFT operator? Seems like an innocent question. Well, quickly people understood that at leading order in large N, for most purposes, a pretty good answer is a single trace operator in a short multiplet. Now, in our setup, we have an orbifold CFT. So a trace means a sum over all the copies of the theory, resulting in an operator which is invariant under the Sn discrete gauge group. However, there are 1 over n corrections to this identification involving multi-trace operators, and this is important for today's talk. So it's important because the multi-trace terms contribute at leading order in extremal correlators, and also it will play an important role in our analysis. And so this mixing between single and multi-traces is going to be a key part of the story that we have to tackle. So this question has been considered by quite a few people since the early days of holography with various bits of progress. But it was only relatively recently that a surprisingly simple prescription for how to deal with this was put forward in the context of ADS5. And the prescription was, okay, consider all the set of all multi-trace operators, and then consider the CFT operators that have vanishing two-point functions with that full set of multi-traces. That defines a set of operators, and the proposal is that that is the single particle basis of operators in the CFT. And for the half BPS short multiplets in ADS5, this fixes the mixing uniquely and has passed several checks. So this gives some specific 1 over n coefficients for these multi-traces. Now in ADS3, that's not quite enough because there is additional mixing purely at the level of single traces. And this has been studied before. So it's not enough to say, okay, I fix all the multi-trace admixtures. Also, just purely at the level of single traces, there is mixing due to operators having degenerate quantum numbers, which you have to disentangle to say this combination of operators is dual to this single particle supergravity state. So in ADS3, we're going to have to combine both of these mixings to solve for the single particle basis. Okay, so let's do that.
Sorry, may I ask a question?
Sure.
Massimo Bianchi.
Hi.
The question is, resolving this mixing means taking into account string corrections, that is 1 over n corrections.
Well, naively, yes, but we will need this already at the supergravity level. So, you might have thought that, this, in the usual dictionary, 1 over n maps to, well, in fact, to quantum corrections. But actually, it's necessary here for correlators which are either extremal or where this multi-trace is going to be the dominant source or the only source of the expectation value, that even at the level of supergravity, we need to discuss this mixing.
Okay, thanks.
Any other questions? Okay, so the general formalism of precision holography, in particular in ADS3, it goes as follows and goes back to a set of nice papers by Skenderis, Taylor, and Kannetscheider from 06 and 07. So the recipe, I'm going to sort of outline how you do this in words rather than give you all the details. But the recipe is to first compactify from 10D to 6D and look at configurations which are asymptotically ADS3 times S3. Then we take an asymptotic expansion and linearize around the vacuum solution. After that, we KK reduce on the S3 to three-dimensional formalism, which involves expanding in S3 harmonics. When we do that, we need to then diagonalize the three-dimensional linearized equation of motion and then eliminate cubic derivative couplings of supergravity fields by appropriate field redefinitions. One needs to identify appropriately the gauge invariant or covariant combinations of these fluctuations, and one has the option of doing some partial gauge fixing. And finally, then one can compare with the CFT, where we start to do the obvious thing, which is match quantum numbers of the light operators to these bulk fluctuations. And as I mentioned, that results, part of that is straightforward, but then part of that you have to resolve this mixing, firstly among the single traces, and then between the single and multi-traces. And when you've done all that, which is already hard work in itself, then you need to compute the normalization coefficients in the dictionary between gravity and CFT, according to how you normalize the operators on one side in the CFT and the bulk fields on the other side. So this is the general recipe. And so let's give a little bit of how that works in the bulk. So in the superstrata example, the field content in 6 dimensions is minimal supergravity coupled to 2 tensor multiplets. So the bosonic field is the metric, 2 scalars, and 1 self-dual 3-form and 2 anti-self-dual 3-form field strengths. This theory can be embedded into a larger 6-dimensional theory, which is useful to do because the spectrum of fluctuations was studied before. And it comes with its own notation, which is not so important. But simply to say that there are, there's a larger field content of this theory. And so in the notation of that formalism, M of these, the index M of these scalars equals 5, corresponds to the minimal supergravity content. And then there's another index R, which for us will be 6 and 7. So our 3-form field strengths will be G5, G6, G7, and the scalars 5, 5, 6, and 5, 5, 7. So this is all just connecting various notations. For the supergravity, for the superstratum people, the link to notation which is more familiar with you is as follows. So G5 and G6 are related to G1 and G2, which in turn are related to Z1, Z2, θ1, θ2. G7 is related to G4, which is related to Z4 and θ4. So hopefully this can give you a handle. And if you're not familiar with this, all you need to know is that we're going through this procedure of identifying the fluctuations that are relevant. So then we expand in S3 spherical harmonics. And again, if you're not an expert, all you need to do for today's talk is keep an eye on this couple of vectors here, Z mu, with labels 6 and 7. So Z6 and Z7 are going to be my main characters in the story. The rest of it is included for completeness because although Z6 and Z7 are going to be the examples I deal with later, there's a whole other story about the scalars, phi, u, and pi, and so on.
So your little g's with 3 indices are the gauge field strengths being expanded, right?
Exactly. These are 3-form field strengths. So all you need to know is that these vectors Z6 and Z7 come from the 3-form field strengths with 1 index on ADS and 2 indices on the S3. So that gives a vector in 3 dimensions. and the rest of it is various decompositions into spherical harmonics, which are either scalar or vector in this case. Okay, and so at the end of the day, we end up with, in the sector we're interested in, we end up with some three-dimensional scalars and some three-dimensional vectors. And these are going to be the appropriate gauge invariant combinations that generalize these fields are going to be the quantities in the bulk which are dual to the correlators in the CFT that we're going to study. So this notation here just means that there is some linear combination with some k-dependent factors combining these three-dimensional fields into nice scalars and vectors that we can study. Okay, so that was on the bulk side, and now we're going to discuss the CFT operators that are the light operators. So firstly, at dimension 1, we are interested in chiral primaries. So firstly, we have R symmetry currents, J and J bar. So these are dimension 1, 0 and 0, 1. These are made in the free field representation out of these elementary fermions that I mentioned at the start. And these are organized into, again, there's 4 of them with each of these indices taking value plus or minus or 1 and 2. And these are all single trace operators on this slide. So the trace is exactly this sum over copies here. R labels the copies. And so what we have here is an SU2 R symmetry current, JR on each copy R, and then we sum over the whole CFT to get an invariant, and there's only a single sum over the CFT, so this is a single trace operator. Other examples are a twist 2 chiral primary operator with this particular relation between the dimension and the twist. And this is a 1/2, 1/2 operator. Here we have the twist 2 operator, which links together the strand R with strand S. And again, we have a single sum over the CFT that makes a single trace operator. And then we dress it up with some spin fields to make the appropriate chiral primary. And finally, there's a twist 1 operator in the sector, again with dimension 1/2, 1/2, which is one left moving fermion and one right moving fermion made into some particular linear combination. These are all single trace operators, and the holographic dictionary was studied in these 2 papers that you see here. Okay, good. So the main part of my talk is all going to be about dimension 2 operators and their superdescendants. So let's first examine the single trace operators that are dimension 1, 1 chiral primaries. So one way we can make a 1, 1 operator with a single trace is to have a copy of a left current and a right current, J and J bar, both acting on the same copy of the CFT, and then summing that over all copies of the CFT. We also have a twist 3 chiral primary with of the same kind of sigma type, with this relation between a weight and twist. And this, again, is a single trace. We take any 3 copies of the CFT and we combine them in a symmetric fashion with a single sum over the CFT, and we dress it with charge to make a chiral primary. And finally, there's a twist 2 operator with the same 1, 1 dimension. And this is the O2 operator. So it's the analog of, if I go back, this O operator, which was the one which was related to the 0, 0 strands, simply with a twist 2. So we make the twist 2 operator and then act with O on each of the strands. So these are all the single traces in the 1, 1 sector. But we also have this complication of the double trace operators. So by fusing the single trace operators, we get products of, let's say, sigma 2 with sigma 2, where now our sum over the CFT is over 2 separate combinations of strands. So this is, all of these are going to be double trace operators. All of these sums you hear, all of these sums you see are going to be sums over 2 different things. So for instance, on the J's, we take J on any one copy that you like and a J bar on any other copy that you like, and then sum over all copies. So this is simply what you get when you take the product of the single trace J and the single trace J bar. Okay,
Is there any regularization you have to do when the two copies are the same and these operators coincide?
I mean, it's the usual point splitting thing. So
Okay,
if there is, you just subtract it, and yeah. So that's how it goes. Okay, so the thing you should notice on this slide, or the thing you should keep track of, is that as you know, this O operator here is sort of on a different footing from the sigmas and so on, because it has this is related to the 0,0 strands. It's related to the T4, and so in particular, there's sort of a hidden SO H11 of the internal manifold under which this is part of a vector representation rather than a scalar. So anything where you see a single copy of O is going to mix differently to the other operators. That will become clearer in a moment. So the mixing, I already started to say that essentially everything that is allowed to mix by symmetry does mix. And so the structure in the sector of dimension 1,1 is that there's a separation according to this O operator and its twist to analog O2. These can mix with each other, but with nobody else, and vice versa. So there's basically two distinct sectors of mixing, which is allowed by the representation theory. And so out of these combinations, we end up with, so the multi-traces will always be there along to the right, but out of these operators, we will get some particular single particle combination, O2 tilde, which is a linear combination of these operators. And then out of these 5 operators in the first line, there will be 3 double traces, and now 2 single particle operators, which are linear combinations of all 5 of the single and double traces in the bracket. So as I said, the single trace mixing was understood before, but what we're going to do new is solve for this mixing between the single and double traces, and then use that for holography. So a little bit more explicitly, for instance, this sigma 3, you can write as some general linear combination of all 5 operators in this bracket. And we solved for, so C1 and C2 were understood before, but we've solved for all of these coefficients explicitly as numbers which are now part of the precision holographic dictionary, which can be used on any state. Okay, so to supercharge this dictionary, or to study supercharged superstrata, we need to expand further by considering the superdescendants. And the ones we're going to focus on are the light operators obtained where we act with GG. And every time I say GG, I'm going to mean this particular combination that I mentioned earlier in the talk, acting on either sigma 3 tilde, meaning the single particle combination, or O2 tilde, this single particle combination. So because of the whole structure of the dictionary and the algebra, we don't have to, after we've solved for the single particle sigma 3 tilde, we don't have to solve again for the GG sigma 3 tilde. We can simply apply the supercharges, and the same coefficients will be there in the dictionary. And these will be dual to single particle excitations. So these sigma 3 tilde can be used to probe superstrata, the non-supercharged, and then these will be essential for the supercharged superstrata. So putting it all together, the overall structure of the dictionary is as follows. And again, if you're not familiar with all these details, just keep an eye on Z6 and Z7. These are the vectors in 3 dimensions, whose leading terms in the asymptotic expansion is are dual to the sigma 3 tilde, GG sigma 3 tilde, and the GG O2 tilde. And so amongst that dictionary, there are all these dimension 1 operators that I said were understood before. And then these are dual variously to ADS3 scalars and vectors. So I won't go into all of the details in lieu of time. So once we've done all that and sort of figured out the entries in the dictionary and who corresponds to what, we then compute the coefficients in the dictionary. So we specify the normalization on both sides, both in CFT and gravity. The relative coefficients that I've just described can be obtained by a purely CFT computation if we use the single particle basis. In our first paper, we actually used a different technique, and we calibrated this against the established dictionary for two-charge microstates, and both of these give equivalent results. So then the overall coefficient in the dictionary is a separate computation which we bootstrapped through this two-charge dictionary, which is well established, through the original superstrata and to the supercharged superstrata. And at every step, a strong constraint on this whole formalism is that the coefficients in the dictionary can only depend on moduli or other parameters and can't depend on any labels of the state or labels of any family of states you might be considering. And in fact, if you normalize in a nice way, these coefficients only depend on large n and some pure numbers like 2 and square root of 3. Okay, so let's assume then that we've computed all these single particle combinations, we fixed the relative coefficients in the CFT, and that we also identified these gauge invariant or covariant fields in the bulk. Then the last step is to compute these overall coefficients, and then we can test supercharged superstrata. And so I'll give you 3 relatively quick examples, and then I'll wrap up. So the first example is a supercharged superstratum, which is a single mode with these particular values of k, m, n, and q. So n is a free parameter, and I've chosen some particular combination. This is one of the original supercharged superstrata. And so any example of these solutions in the bulk and these states in the CFT can give me a computation which compares the CFT expectation value of the light operator with the leading fall off of the appropriate dual 3D vector with some coefficient alpha, which you have to compute. A little bit like effective field theory, you put some arbitrary coefficient, you make a scattering experiment, you fix that value, everything else is a prediction. And alpha then has to depend only on big N, as it will do, and it can't depend on little n, for instance. So this works beautifully. You get some particular value of alpha, and this is a relatively simple example where the operator that gets a VEV is precisely the operator that takes the excited strand and converts it into a vacuum strand. And that VEV, that expectation value is non-zero because this big coherent sum allowed for different values or contains different numbers of the vacuum strand and the excited strand, so that there's a non-zero value for the correlator of an operator which simply converts the excited strand into the vacuum strand. And in this example, it's exactly the single trace part of the operator that corresponds to the expectation value. So great, we didn't even need to go through all this blah blah about the multi-traces for this particular example, but it works. Where the multi-traces are really important is in examples where we can actually probe the coiffuring in the bulk. So let's consider a more general family of states. This is a set of states with 2 excited modes in the bulk, with the one with m equals 0 or m equals 1, and we'll use some different values of n for the mode without the j plus and the mode with j plus. So when the values of n, which we'll call m, b, n, and d, are not the same, this is a prototypical example of these horrendously difficult original superstrata where it was very unclear how to make the solutions in the bulk for quite some time, and it required this new coiffuring. Okay, so if we take one example, then we can compute the coefficient beta in this dictionary, which now is the other vector in ADS3 Z6, and the expectation value is this combination GG sigma 3 tilde. The result is very nice. We get alpha equals beta, which is expected by the symmetry on the supergravity side that rotates the tensor multiplets among each other. And again, you can just take one particular choice to fix beta, and the rest is a test of the dictionary. But in particular, the mixing between single and double traces is crucial here, because the contribution to the expectation value doesn't have any there's no contribution from the single traces. These are just 0 on this particular state. The expectation value is completely determined by this GG00. And so this mixing between the double traces is crucial. In particular, this coefficient C3 is going to control the VEV. And this conceptually is how we see a quadratic structure in the CFT completely analogously to this quadratic interaction of supergraviton modes in the superstrata. And so this, for me, conceptually is very nice. We see the CFT insight into coiffuring, and there's actually a simpler example that we had in the first paper, just with the double trace 00. Okay, the last example is a test which tests, now we fix the dictionary so we can test the supercharged superstratum proposal once more. And we can also test the mixing of terms in the CFT. This is an example of states where we again have a double mode solution, one supercharged mode and one original superstratum mode. So this is sometimes known as a hybrid solution or hybrid set of states. And here it's a feature of the solution that the vector Z6 is switched off. This leading term is completely 0. And so it had better be the case that the CFT VEV is also 0 for this single particle combination. And this is an example where both of the single traces have non-zero VEVs, and one of the double traces is also turned on, has a non-zero expectation value. And there's a delicate cancellation, which gives a very nice non-trivial 0. So the punchline is that all the examples pass highly non-trivial tests, which demonstrate agreement between gravity and CFT to the precision that we can probe. Okay, I'm a few minutes over time, so let me wrap up. We have refined and extended the precision holographic dictionary in new sectors of light operators, resolving the mixing between single and multi-traces. We performed precision holographic tests of superstrata. It works beautifully. Finding this agreement does not and cannot prove the proposal because we're only looking at a limited set of expectation values, but it is supporting evidence for it. And there's plenty of scope for further generalization, and I'll leave it there. Thank you.
Well, thank you, David. That's fantastic. So, questions, comments?
Can I ask a question?
Sure.
So you said there is this, so I'm not entirely familiar with this coiffuring relation, but what exactly does it correspond to in the CFT? Which condition do you have to impose on the CFT side?
So on the CFT side, there's different ways of understanding these relations. So they're all algebraic relations between parameters. The simplest way to describe how the coiffuring works is, firstly, your ansatz has to be general enough in the supergravity that you have enough freedom to arrange the smoothness. So if you hadn't, for instance, in this example I presented, if your ansatz in the supergravity did not contain enough freedom to have the Z6 turned on, then you would not be able to arrange smoothness even in the first place. So we wouldn't even be talking about the algebraic relations on parameters because you didn't realize you had to generalize your ansatz to even include another parameter. And so that was the problem at the start, was this field hadn't been turned on, and the ansatz wasn't general enough to arrange smoothness. So then in the CFT, it's simply the fact that this expectation value is non-zero due to the double trace mixing. That tells you, hey, that means that whatever the bulk dual solution to this state is, must have this field switched on, and in some particular amount. And then in the gravity, the second step is not just switching this field on in the ansatz, but with a particular strength that combines quadratically with other parts of the supergravity solution.
And that strength is then related to the coefficient that appears in this sort of double trace correction term to the single trace operation?
Yes, exactly. Yeah. Mm-hmm.
in the supergravity, this has been sort of part of the history of the thing. The conformal field theory tells us that there are new states that we have to activate, and in supergravity we run into occasional roadblocks in constructing smooth solutions, and these processes have gone hand in hand. And supergravity smoothness again and again comes about through activating the right degrees of freedom and then tuning coefficients in the CFT to match perfectly. And it's amazing. Sometimes the supergravity is being driven by the CFT, and other times it's the other way around. But the bottom line is that precision holography, the ADS CFT, turns into a smoothness requirement in supergravity, which is really cool. It sort of, for me, just sort of really reinforces the sort of correctness of the attitude that microstate geometries or fuzzballs is what you're looking for, and not singular solutions.
Can I ask another question? So you defined the single trace as being somehow orthogonal to all the multi-trace terms on the CFT side.
Single particle, yeah. So
it's in the for the 2-point function. But when you then look at an n-point function, is the 1/n scaling, how does the 1/n scaling behave for these? I mean, does it behave sort of like a canonical single trace operator?
It depends on if we talk. So it's the usual story about extremal correlators versus non-extremal correlators. So I didn't go into that in my talk, but it's been understood for some time that all of these double trace corrections, essentially these factors of C3 contain some powers of 1/n to some 1/2 or whatever it is. And so for generic non-extremal correlators, these do not contribute, and only the single trace operators control the correlator. It's a leading order in 1/n. However, for extremal correlators, these multi-trace contributions, even though they come with 1/n coefficients, they contribute at leading order in the log n. And so they're crucial for extremal correlators in particular.
So how does one understand that they contribute at leading order? Because they somehow contract in some way to cancel the 1/n? Or?
Exactly, yeah. So the contribution will exactly cancel the 1/n. The contribution of the contraction will counterbalance exactly the 1/n. Only when you have an extremal correlator such that you have some resonant Wick contractions in some sense.
And you're saying for non-extremal correlator that doesn't happen? They're really subleading?
Yeah.
Okay. Thanks.
Any other questions? So I remember having a conversation, I think, with Rastelli quite a few years ago when they were trying to do precision holography of ADS 5 times S5. And there's this very old story. Everything you said is reminiscent of an old story in consistent truncation. So in consistent truncation, what one is trying to do is one's trying to decouple a lower dimensional supergravity theory out of all the Fourier modes of a higher dimensional supergravity theory. And when you do it in toruses, it's trivial. But when you do it on spheres, it's highly non-trivial because the lower supergravity degrees of freedom are encoded not just in the lowest harmonics, but in progressively higher harmonics in a very particular way. There are all these warp factors and extra powers of harmonics. And so consistent truncation on spheres is highly non-trivial. And what it really means is that if you think of the lower dimensional degrees of freedom of the supergravity, they are actually encoded not just in the leading harmonics, but in very precise tunings of higher and higher harmonics in the theory. And so this process of where you start saying, okay, to actually construct the single particle state, you've got to make this very particular combination of single trace and double trace operators, is so extremely reminiscent of this statement that a lower dimensional supergravity theory, degree of freedom is not just the lowest and singlest, stupidest harmonic you can make. It's a very non-trivial series of higher harmonics. And I've often wondered whether these two observations are in fact, some sense, dual to each other. I don't know whether you see any evidence of this here.
It's a nice question. I think maybe the only useful thing I can say in real time is simply about the structure of this holographic dictionary, that I didn't go into the details about this K parameter, but this is effectively the radial fall off and also the spherical harmonic quantum number that controls these gauge invariant fluctuations in the bulk. So the the higher values of K are higher fall-offs of the various modes, and these are the combinations which are, if you like, the good combinations for holography that are dual to these specific single particles. So how that fits exactly in the consistent truncation story, I guess you'll be asking what combinations of ADS3 fields you can combine into some consistent truncation, and what subsector of the CFT you might be interested in.
So one of the consistent truncations that Daniel and Robert and I worked out recently, but it's not the one that's relevant here for the thing you're doing, because we only did the 10N or 11N. But I believe, although it's certainly not been proved, but I have evidence that the 21N theory actually also has a consistent truncation to 5 dimensions. So, but I think there are broader consistent truncations in here, but I've often wondered whether it's more an intellectual question of whether the question that's being asked in the supergravity, that how do I encode the lower dimensional supergravity degrees of freedom in all the harmonics of the supergravity, whether this is a statement about operator mixings in the CFT and orthogonality of the single particle state to all the other crap is the statement that the lower dimensional theory decouples from everything else.
Indeed, it certainly has the same flavor. So it's, yeah.
I can't
discuss.
Okay. Any other questions or comments?
Can I ask something?
Please go ahead.
So for 00 strand superstrata, so we have now a very good understanding of this coiffuring from the gravity side and also the CFT side. But there are other families or sectors of the superstrata that we have not been able to construct. Does this technique say something about those new families, like what kind of coiffuring we have to consider, or maybe does this point some particular simple sector which can be constructed relatively easily? Is that?
Yeah, thank you. It's a great question, and this is my number one question that I want to know, and I want to talk to supergravity people about. And I sent Nick this question a couple of weeks ago, and I have it on the slides for tomorrow's discussion. But just briefly, yes, I think it's a great question. So far, all of the CFT technology in the last couple of papers has been coming a little bit behind the supergravity program, where the supergravity constructions have been able to take enough input from the CFT to basically get very far for 00 strands, and we are verifying all of that in this work.
Yep.
But this has the potential to be extended into sectors where the supergravity constructions are not yet understood exactly how to go about it.
Right.
And so in principle, yes, this program could be pushed into new sectors. I think, with what I've sort of described today in terms of these new sort of conceptual improvements in terms of single particles overlaid to the existing, understanding of how to go about precision holography, I think this is ripe for pushing further. And so I want to discuss more with people who've been trying to construct some of these supergravity superstrata of different types, what your sort of shopping list is for input from the CFT. And then we can maybe have a situation where the CFT leads the way for more general supergravity strategies.
Can I ask apropos that you perhaps maybe make a list of things that might be doable in terms of the perturbations you can treat, and then
I think this needs to be done on both sides. So
yes.
I think there's some fruitful conversation that can be had here. As while I've said it, conceptually, I think it's straightforward. It should be said that on an actual practical technical basis, you do need a strong graduate student or students, and so there's been a tour de force of my student Sami, and so there is quite a lot of work to actually carry out this this program. But if there's motivation from the supergravity, then that will give us motivation to push and see where we can go with this.
Okay, I'd like to take at least a 10-minute break, so there's about 3 minutes. So any last questions or last comments or any other issues? Masaki, any follow-ups? Okay, so let's take a break. David, thank you very much, and we'll resume at 6:15 for the panel. And for the panelists, I think we just go in